Hello everyone. Today, in continuation with the previous topic of electromagnetic induction, we will study about first induced EMF and induced current, and second we will study about the motional EMF. In induced EMF and induced current, we will talk about the expression for induced EMF based on Faraday's and Lenz's law, expression for induced current, expression for charge, factors affecting the magnitude of induced EMF, and applications. In motional EMF, we will study about the expression of motional EMF from Lorentz force, and Fleming's right hand rule. Now let's recall what we have studied earlier. We have studied about the magnetic flux, which is equal to BA cos theta. We have studied about the induced EMF given by Faraday's and Lenz's law, which is equal to minus d phi by dt. Minus sign indicates that the induced EMF will be such that it always opposites cause. The magnetic flux can be changed by changing the strength of the magnetic field, cross-sectional area, the orientation of the magnetic field, and any of the above combination. These things you have studied in the previous topic. Now today we will talk about induced EMF. As you know, EMF which has been induced means which has been introduced in the circuit when the magnetic flux linked in it is changing. So important thing is that we are not talking about the ordinary EMF, we are talking about the induced EMF which has been generated by the change in the magnetic flux linked with the circuit. So children, here the word change in magnetic flux is very important because we are getting this EMF only when the magnetic flux is changing. For the expression of induced EMF, we have already done in Faraday's and Lenz's law. This EMF is given by minus phi 2 minus phi 1 upon T. Phi 2 minus phi 1 means the change in the magnetic flux. Phi 2 the final and phi 1 the initial upon the time duration in which that flux is changing. And the minus sign which is preceding it is indicating that it will oppose its cause. If the flux is changing for a small amount, by a small amount for a small interval of time, then EMF is given by minus d phi by dt, small change in magnetic flux in small interval of time. Now this is for a single turn of the coil. If we have n number of turns in the coil, as you can see in the diagram, there are 3 turns in the coil. If the number of turns are n, and then the EMF will become n times d phi by dt, and of course negative sign will be there. That is minus n d phi by dt, or it will become minus n phi 2 minus phi 1 upon t. So the induced EMF will develop only when the flux is changing. As you can see in this diagram, when the north pole is approaching towards the coil, the induced EMF and the current develops in the coil because the magnetic flux is changing. Now about the induced current. Induced current means that the current that flows because of the induced EMF. When we are getting induced EMF and if the circuit is complete, then the current which flows in the circuit is called induced current. So in EMI, the EMF so produced or the current which is flowing in the circuit are said to be induced current or induced EMF. The expression for induced EMF, induced current is given by induced EMF divided by R, the resistance offered by the circuit. So we can say that I can also be written in terms of the rate of change of magnetic flux, that is minus 1 upon R times d phi by dt. Again, minus sign is indicating that it opposes its cause. Similarly, we can have the expression for charge. As we know that I is given by dq by dt, the rate of flow of charge. So this can also be written as dq by dt can be written as minus d1 upon r d phi by dt, or simply we can say that dq is equal to minus d phi by r. Now, the factors affecting the magnitude of induced EMF. First is we will talk about the condition for to have larger current. How we can produce a larger current in the circuit. This can be done by moving the magnet faster in and out of the coil, towards or away from the coil. If the speed, if the relative velocity is more, then larger current can be produced in the coil. Secondly, if the magnet is strong, because if the magnet will be strong, more magnetic field lines it will be having, and more flux will change in the when there is the movement of magnet. So the strong magnet can also produce larger current. Third, we can increase the number of turns in the coil. If we increase the number of turns in the coil, the EMF, which is N times d phi by dt, will increase, and so the induced current will increase in the circuit. Or we can have a soft iron core which can be inserted in the coil to increase the current, because soft iron core is made up of ferromagnet, and ferromagnet attracts the field line towards it. More and more field lines will cross through this soft iron core, so more and more field lines will cross the coil if the iron core is inserted in it. So these are certain ways by which we can increase the current, or we can have a larger current produced in the circuit. Another thing which is very important is no EMF is produced. Under what condition EMF will not produce? First is if the magnetic field is stationary, maybe outside or inside the coil, then there will be no EMF. If field is not changing, if field is stationary, means the field is constant, so it will not produce any EMF. Or if there is no relative movement between the magnet and the coil, neither the magnet nor the coil are moving, there will be no EMF produced in the circuit. Now let's talk about certain application. The major application is the power generator. We are getting electricity, we are getting power, electrical power, only because of this Faraday's law of electromagnetic induction. The electrical generators, AC generators, DC generators, you must have studied in the earlier classes, they produce EMF by moving the conductor. The conductor is moving in the orientation. Here we say the orientation of the coil is changing, and we are getting the change in the magnetic flux, or we are getting induced EMF and hence induced current. Another application is electromagnetic blood flow meter. In this, the rate of flow of arterial blood can be detected. A magnetic field is set up across the artery and the EMF induced in the flowing blood. So knowing the induced EMF, knowing the magnetic flux, we can estimate the rate of flow of artery blood. Third very important application is transformer. You must have seen transformer on the roadside near your streets where you live, or near the lanes. Many roadsides you must have seen transformers. So these transformer, they are basically based, the principle of transformer is based on electromagnetic induction. In the previous topic, we have studied that if the current is changing in the primary coil, it induces a current in the secondary coil. So this is the main concept of transformer. The primary coil current moves back and forth across the secondary coil. The moving magnetic field caused by the changing field will create a current in the secondary coil. So this is the basic principle of transformer. Another application is a microphone. Microphone, we know that in the microphone there is a diaphragm. So when the sound waves enter the filter of the microphone, a diaphragm is situated in the filter. Inside the filter there is a diaphragm. The diaphragm, the sound waves vibrate the diaphragm. When the sound waves it creates the vibration in the medium, and so the diaphragm also starts vibrating, which in turn move the coil, and the coil is wrapped around a magnet. So the movement of the wire in the magnet will create a current in the wire. So this is how the microphone works. So these are some major applications of electromagnetic induction or induced current, induced EMF. Now there are different methods for the prediction of induced EMF. As we have studied earlier, that it is depending upon the rate of change of magnetic flux. So as the magnetic flux depends upon the changing magnetic field, a changing area of the coil, or by changing the orientation of the coil, so induced EMF also depends upon these methods. So induced EMF is given by minus d phi by dt, where phi is magnetic flux equal to dA cos theta. Now out of these three, by changing the magnetic flux, by changing the cross-sectional area, or by changing the orientation, here we will discuss the second one, that is the changing by changing the cross-sectional area. The EMF so produced is known as motional EMF. So now we will talk about the motional EMF. What happens that when the magnetic flux is changed, how it is changed? By changing the area of the loop, which is acted upon by the magnetic field. Then an EMF is introduced in the circuit. So in the motional EMF, the magnetic flux is changing by changing the area of the loop. The EMF which induced across the ends of the conductor due to its motion. The conductor is moving. As the conductor is moving, the area is changing, and as the area is changing, magnetic flux is changing. So the induced EMF which develops is known as motional EMF. Why it has given the word motional EMF? This is an induced EMF. But why we are calling it motional EMF? Because it is due to the movement of the conductor so as to change the area of the loop. Now let's talk about the expression of motional EMF. You can see that there is a rectangle, and in this rectangle, this PQ arm, a conductor which can slide, and the rest of the arms are fixed. So PQ can slide inside or outside these metallic rails. So a conductor PQ is moved inward. Let first we say that it is moving inward with some velocity v. Assuming that there is no loss of energy due to friction, we are avoiding the concept of loss of energy, energy dissipation due to friction. As the conductor slides towards left, the area of the loop PQRS decreases. It's very much clear to you that this area, initial rectangle, is PQRS. When PQ is moving towards the left side, then the area enclosed by this loop will decrease. So this decrease in the magnetic flux linked with the loop. So if the area is decreasing, magnetic field linked with the loop will also decrease. As a result, EMF will set up across the ends of the conductor PQ. So the PQ conductor is there, and here the EMF will induce, and this is due to the movement of the conductor. So this movement induces a current, and if there is an induced EMF, it will give rise to induced current. So if the length RQ is X and RS is L, the magnetic flux encloses by PQRS will be BLX, where LX is the area of the loop. As the conductor PQ is moving towards left, the value of X is changing, is decreasing with respect to time. The rate of change of flux will induce an EMF which is given by minus d phi by dt, or it is equal to minus BL, because B and L are independent, not changing with time, can be taken out from differentiation, will be equal to B minus BL dx by dt. This dx by dt is nothing but the velocity by which the conductor is moving towards the left side of the rectangle. This dx by dt is equal to minus v. Why minus v? Because the distance is dx is decreasing with respect to time. So finally we say that the EMF minus will vanish, and we say that the EMF so generate in the coil is equal to BLV. So this BLV is known as the motional EMF, which depends upon the magnetic field, the length of the conductor, and the velocity by which the conductor is moving. So we are getting an expression for emotional EMF as BLV. Now, this motional EMF can also be expressed in terms of Lorentz force. Do you remember Lorentz force? What is Lorentz force? A charged particle which, when it is moving in a moving charged particle, is in a magnetic field, then it experiences a force. So from where is the moving charge? Yes, the conductor is moving towards the left side, as we have studied in the previous case. Conductor having free charges, so charges are also moving along with the conductor. So these moving charges in the magnetic field experience a force. So what happens that in suppose the charges are Q in the conductor PQ. So when the rod moves with velocity v, the charge will also starts moving with the same velocity v. So the Lorentz force on the charge is given by QVB, where B is the magnetic field, Q the total charge, which is there in the, let it be there in the conductor PQ, and it is moving with velocity v. Here the velocity and the magnetic field are perpendicular to each other, so V cross B can, QV cross B can be written as QVB. So all the charges experience the same force in the magnitude and direction, irrespective of their position in the rod PQ. Wherever the charges reside in the PQ, they all will experience a same force, because all are moving with the same velocity, all are having like same charges, and all are having moving in the uniform magnetic field, which is also same for all the charges. So all the charges will experience experience same force. Now The work done in moving the charges from P to Q will be given by work done. What is work done? Force into displacement. So work done will be equal to QVB into L, because the charges are moving from P to Q. So work done in moving the charge from P to Q will be given by QVB into L. Secondly, we know that the EMF can also be expressed in terms of work done as work done per unit charge. So the EMF will be equal to work done upon charge, that is again the same expression BLV. So the expression for motional EMF can be expressed in terms of Faraday's laws or in terms of Lorentz force. And in both the expression, we are getting the same equation, that E is equal to BLV. Now, as the current is induced in the circuit because of the change in magnetic field or magnetic flux, the direction of induced current is given by Fleming's right hand rule. In the previous exam, motional EMF, in the case to find out the induced current, we will apply the direction of induced current will be according to the Fleming's right hand rule. What is Fleming's right hand rule? It's very simple. We take our right hand, stretch our thumb, forefinger and central finger in such a manner that all the three are mutually perpendicular to each other. The forefinger F gives the direction of field. The central finger C gives the direction of induced current, and thumb M, motion, gives the direction of force. So if we know force, the magnetic field, we can find out the direction of induced current. So this is how we can apply Fleming's right hand rule to find out the direction of induced current. So this is all about the topic. Let's have a conclusion. The time varying magnetic field generates an electric field. Electric field produced by static electric charge have property different from those by time varying magnetic fields. So electric field in the static charge is different from the electric field which we are getting due to time varying magnetic field. Charges in motion, that is current, can exert force or torque on a stationary magnet. A bar magnet in motion, or generally a changing magnetic field, can exert a force on the stationary charge. So if there is the bar motion, a bar magnet in motion, then it can exert a force on a stationary charge. So in all, we can conclude that the electricity and magnetism are related to each other. The changing magnetic flux give rise to electric field. The changing electric field give rise to magnetic field. So electricity and magnetism are interrelated to each other. So this is all about today's topic. Now have some assignments. In this figure, this is the question from NCERT book, and it's a very important question. In figure shows the planar loops of different shapes moving out or into the region. You can very well recognize with the help of these arrows. Then magnetic field which is directed normal to the plane of the loop, away from the reader, away from us. Determine the direction of induced current in each loop using Lenz's law. So here, if the flux is increasing means if the coil is moving inside the magnetic field, the flux is increasing, the direction of current will be in the counterclockwise direction or anti-clockwise. If the flux is reducing, then it will be in the clockwise direction. This concept you have to take for giving answer for such type of questions. Second question, very important, another very important question. Question number 2. A metallic rod of 1 meter length is rotated with a frequency of 50 revolutions per second, with one end hinged at the center, fixed at the center, and the other end at the circumference of a circular metallic ring of radius 1 meter, about an axis passing through the center and perpendicular to the plane of the ring. The axis is perpendicular to the plane of ring. A constant and uniform magnetic field of 1 Tesla parallel to the axis or is present everywhere. Uniform magnetic field is there. What is the EMF between the center and the metallic ring? This is the case of motional EMF. E is equal to BLV. Here you have to write V in terms of angular velocity, and you can get the answer. Next question. A rectangular wire frame shown below is placed in a uniform magnetic field directed upward and normal to the plane of the paper. The part AB is connected to the spring. You can see in this diagram, AB is connected to the spring. The spring is stretched and released when a wire AB has come to position A dash B dash. When it is coming to A dash B dash, the spring has been released. How would the induced EMF vary with time? You have to neglect the damping. So when it has been released, what will happen? It will start moving, having to and fro motion. And if we neglect damping, we can find out the induced EMF varying with time. So this is all about today's topic. Thank you so much.